welcome to Intermolecular Forces, Solids and Liquids. My name is Dr. English. Today we're going to be talking about characteristics of liquids. Specifically, we're going to look at, the general characteristics of liquids: vapor, evaporation, rates of evaporation, vapor pressure, and normal boiling point. Characteristics of liquids. Unlike solids, the particles that make up liquids are in a random arrangement. The forces between the particles are strong enough to hold them together, but these forces do not lock these particles into a specific position. So if we look at the model on the left, we can see that the solid is in a very orderly fashion, while the liquid on the right is much more disordered. It's not completely taking up the container, but it's taking up the space of the container at the bottom. Particles in a liquid are free to move. Liquids have a definite shape but no definite volume. Particles take on the shape of their container. As with all matter, the particles that make up a liquid are in constant motion, as we can see in the simulation off to the right. The average motion of the particles relates to the average kinetic energy of the particles, which we know is temperature. Vapor. In any sample of a liquid, some of the particles have just enough energy to escape the attraction of their neighbors. If these particles are near the surface of the liquid, they leave the liquid and become vapor particles. The term vapor refers to a gas that is normally a liquid or a solid at room temperature. Evaporation. The process of forming a vapor is called evaporation, and it occurs at the surface of all substances at all temperatures. Rates of evaporation. Temperature. As temperature increases, more particles have sufficient energy to escape the liquid or solid phase and enter the vapor phase. Rates of evaporation. Surface area. A puddle evaporates faster than does water in a bottle, which makes sense. With a puddle, you have a wide area where that water is found. There's a lot more surface area. In a bottle of water, it will evaporate over time, but only the surface of the water in the bottle, and then it needs to come up through the container through that small opening. So a puddle is going to evaporate a lot faster than water in a bottle. Vapor pressure. In a closed system, such as a liquid in a closed bottle, the vapor produced by a liquid exerts a pressure upward from the surface of the liquid. The New York Chemistry Reference Table H shows the relationship between vapor pressure and temperature for 4 different liquids. Each liquid has a different vapor pressure at any given temperature. For all liquids, as temperature increases, vapor pressure will increase. Vapor pressure and boiling point. As the temperature of a liquid rises, the vapor pressure rises until it becomes equal to the pressure pushing down on the surface of the liquid, which we know is atmospheric pressure. At this point, the liquid to vapor transition can occur not only at the surface, like we see in evaporation, but at any point within the liquid. This process is called boiling, and the temperature at which it occurs is called the boiling point. The normal boiling point of a liquid is the temperature at which its vapor pressure equals the standard atmospheric pressure, which we define as 101.3 kPa in 1 atmosphere. On Table H, the normal boiling point for each liquid occurs where the liquid's vapor pressure curve intersects at the dashed line, which is atmospheric pressure. So this is atmospheric pressure right here, 101.3 kPa or 1 atmospheres, but our Y is defined as kPa, which is why our dashed line is 101.3 kPa. And we'll notice that for propanone, the boiling point is 56 degrees Celsius, because here's propanone right here, and the point where its vapor pressure curve intersects that dashed line, that's the boiling point. For ethanol, the boiling point is 79 degrees Celsius, which again, where it intersects right here. Water is 100 degrees Celsius, which we're already familiar with. We can see that it intersects right here. and ethanoic acid is 119 degrees Celsius, so right up here. Obviously, the greater the intermolecular forces are between these different molecules, the higher the boiling point. The normal boiling point of these liquids follows a general trend. The more massive the molecule, the stronger the intermolecular attractions and the higher the boiling point. Now, this occurs as long as you're within the same intermolecular force. Obviously, water and hydrogen fluoride, they both have hydrogen bonding, so their boiling points are going to be abnormally high. But for molecules like H2S, H2SE, H2TE, these all have dipole-dipole forces as their stronger intermolecular force. But as we go from H2S, H2SE, and H2TE, the molecular mass is going to increase. And as the molecular mass increases, the boiling point is going to increase. Same thing with HCl, HBr, and HI. All have London dispersion forces and dipole-dipole forces, dipole-dipole forces being the primary intermolecular force that we're going to see here, but HCl has the lowest molecular mass compared to HI, which has a higher molecular mass. Therefore, HI will have a higher normal boiling point than HCl will. So what did you learn? We talked about the general characteristics of liquids. We defined the term vapor, evaporation, looked at what affects the rate of evaporation, vapor pressure, and finally normal boiling point. Need more help? Feel free to contact me. Have a great day.